Today we introduce a lecture composed of 3 chapters. The lecture entails a first chapter where we are going to talk about physics in urban environments. The second chapter will introduce the second component of the lecture, which is based on urban environmental indicators. Then in chapter number 3 we are going to be using all the knowledge we have been talking about during the last 2 chapters to see how we can classify cities and urban areas in terms of their urban climate zoning. Urban climate zoning, it could adopt similar approaches to those hired by the classical urban zoning, such as building density and land use. So let's start with the chapter number 1 about some physics aspects in urban area. And here we are going to remind you about some basic knowledge. So the first thing we will introduce you to is weather and climate in cities. And then we are going to see how some climate change aspects are more emphasized than others, such as urban warming. Now, let's start with these aspects. We are going to use a term here that is well known to engineers in aerodynamics. The technical term is boundary layer. But here in this lecture, we will be talking about the urban atmospheric boundary layer. So in your opinion, what is it? Or in more simplified question, what is weather and climate in cities and urban areas? First of all, as you can see in the figure behind me, the layer of weather that is important to us, when I say us, I mean inhabitants, decision makers, transportation and buildings end users, and the construction industry, to not mention but a few. Let's see. We are talking about the atmosphere. It means we are talking about fluid dynamics. As you may know, in fluid dynamics, air characteristics are similar to water. Making this analogy, if we could compare water and air, weather and climate are our main focus, and they are contained in a kind of volume similar to an aquarium that is as deep as 100 meters to 3 kilometers. Usually, if you were in a city and if you want to recognize that part of the atmosphere, clouds could be useful. If you look at the sky and you locate few clouds and look at the bottom of those clouds, then the height that separates you from those clouds could be called the depth of the atmosphere that is relevant to us. Climatologists call this part of the atmosphere the urban atmospheric boundary layer.
1, 2, 3, top.
So now, let's look at few details within this aquarium. The top 80–90% of it, which is around 2,400 meters to 2,700 meters in depth, has a lot of turbulences that are convective-based ones, meaning convective forces are behind turbulence patterns seen in this part of the aquarium. And then in the bottom part, which we locate in the surface layer, located of course in the 10 to 20% depth from the surface, it means 300 to 600 meters in optimal conditions. So this surface layer is located near the Earth's surface, just above building roofs. Scientists classify the surface layer into 2 sublayers. The bottom part is called the roughness sublayer. The upper part is called the inertial sublayer. So usually, climatologists adopt mathematical approaches. In maths, to solve problems, we need to reduce their sizes. This is what explains such a classification suggested by scientists concerning that thing where we are living. So of course, in order to solve problems, they try to reduce them. Now let's explain. To understand what is going on in that sink, scientists try to classify layers within it, depending on the nature of airflow, either triggered by thermodynamic forces or mechanical forces. And in order to understand this, there are many tools such as measurements, experimentation, remote sensing, and numerical modeling. In every layer and sublayer of that urban sink, we got specific types of turbulence patterns and governing forces, whether heat-driven and or mechanical-driven turbulence. Talking about numerical modeling, which are very useful to understand what's going on the urban sink, i.e. the urban atmospheric boundary layer, and to predict what's going on to happen in near and far future. So now, in the upper layer of the sink, turbulences are driven by convective fluxes, and this is why we call it the convective boundary layer. In the bottom layer, called surface layer, we got two types of airflows. In each sublayer, we have different types of flow. In the bottom part, once again, turbulence patterns are very heterogeneous. And the reason behind this is that every single building and obstacle from the surface is affecting the airflow. Now, in the topper part of the surface layer, the turbulences generated by the surface, although heterogeneous, they are blending with the rest of the air and it becomes homogeneous. And the technical word in English is advected airflow. So now you can look at the figures in order to understand these classifications. So once again, the upper part of the urban sink is convective, thus called convective boundary layer, and the bottom part is called surface layer, where we got heterogeneous near the urban surface and homogeneous advected turbulences in more upper part. Coming back to numerical modeling, scientists do sometimes neglect the details within the bottom layer, i.e. the roughness sublayer. Why? Because the regime is so heterogeneous, so in that layer they are only interested in bulk parameters without going into details. It means simplifying somehow. So we have been spending some time talking about the atmosphere that is of interest to us while living in urban areas. Now in the following part of this chapter, we will look at the urban warming and temperature increases. As you know, whether local or global warming, increases in temperatures are one of the most visible and investigated phenomena in climate change studies.